Hello everyone, this is the third video related to Higgs coupling, and before making this video I have already made two videos on intermolecular Higgs coupling. So I will suggest you to watch those two videos before watching this one because that will be easier for you to understand this video. In the description box the two links will be given for the intermolecular Higgs coupling. So let's start intramolecular Higgs coupling. So the picture that you are seeing here, that is for inter, right? Because here we have two components. One is alkyl halide, or it may be triplet also, and another one is alkene. Now after this coupling between these two substrate, we are getting this product where H is replaced by this R. Now when it is intra, what is the difference between these two, that is inter and intra? So in this case also same picture we are again seeing, but in this case these two components, one is for alkyl halide or triplet and the another one second substrate is alkene. These two will be connected to each other. That means they will be part of the same molecule. So in the right hand side, the product that we are seeing, these two, that will be connected somehow. Okay. So that is the difference between inter and intramolecular Higgs coupling. So this is intra. Now we will see the regioselectivity in the intramolecular Higgs reaction. So the regioselectivity that we have seen in case of intermolecular Higgs reaction and the regioselectivity that we are seeing in intramolecular Higgs reaction in this video, there is difference. Okay. So in this case, as they are part of the same molecule, that is the alkyl halide or triplet and the alkene, they are part of the same molecule. As you can see here, we have this alkyl halide iodide basically, and the alkene, that is part of the same molecule. Now this is a tether that you are seeing, and it may be any carbon chain. So this is a general structure. There may be any groups also. So we are trying to understand it with a general structure. So as they are present in the same molecule, so that is why the question of exo and endo arises. Okay. So whether the connection is that is the double bond, after the addition the double bond will be outside the newly generated CC bond or inside, depending on that we will have exo or endo. So first of all, this PDI bond, that will be broken and there will be formation of PDI. So for simplicity the I is omitted, but you can also write it in this way. Now if it is endo, that means the CC bond formation that you can see here, that is after cleavage of this carbon PD, this carbon and this carbon will be connected, and the PDI, now that will be connected to this carbon. So that you can see in the right hand side. So that is the endo closure. But if it is exo, now what will happen? Now this carbon, that will be connected to this carbon, and PDI, that will be outside. That means you just have to focus on this. So in this case we are getting smaller ring if you consider the same substrate, and if you compare the ring size for exo and endo, here we are getting the smaller ring. So here we have to remember that the transition state for the exo closure in reactions that are forming small rings that are lower in energy, when we are comparing the endo transition state in the same reaction, and that is because of the tether length. So longer and more flexible chains are needed, that is longer and more flexible chains are needed to adapt the proper conformation for endo insertion. So this is the reason. And in exo closure we can also see that the bulky PD complex, that means the PDI part, that is this part, along with there will be also ligands present, though those are not shown here because of simplicity, but that bulky palladium part, that will be ending up on the less hindered carbon when it is exo closure. That you can see here, that in the exo closure, now palladium, that is part of here. So we are getting CC bond here, and after this CPD bond formation, the PDI, that will be connected here. And that is the reason now the double bond, if you look at the final product, that is outside. That is the exo product. But if it is endo product, the final product, now the double bond, that is not protruding outside, it is a part of the ring. So that is why it is larger in size compared to the exo product. Now we will see the actual example. This is the previous one, that is the general structure. Now you can see the actual molecule. So in this case, first this Ci carbon iodine bond, that will be converted to CPDI in presence of palladium complex. And you can see from the color, the red one, that is for the 6 endo. Why it is 6? Because after CC bond formation at this position, there will be a 6-membered ring. And the PDI part, that is now connected at this carbon, which you can see here. Now further what will happen, that is the removal of PDI along with hydrogen, beta hydride elimination, that is not shown here, because we are just trying to understand what is the difference between exo and endo, that is the regioselectivity. But if it is exo, now the CC bond that is forming inside and the double bond, CC double bond, that is now outside. So after the addition, the PD along with this I, that will be outside. So here we are getting 5-member ring. This is a newly generated carbon-carbon bond with blue color, because that is for 5 exo. So in the same molecule, you can see 5-member ring we are getting when it is exo, and 6-member ring when it is endo. So we can draw this conclusion that ring closure is highly exoselective when you are getting 5-member, 6-member or 7-member rings. Now here we have an example where the product that you are seeing in the right hand side, that is actually endo product. Now why it is so? Because after this Ci, it will be converted to PDI. Fine. Now this PDI, if this carbon, it is now connected with this one, that means PDI will be somewhere here. And then there is finally generation of CC bond. But if you consider N value, that is this value, if you consider equal to 1, then we are getting 1, 2, 3, 4, 5, 6, 7-member ring we are getting when N is 1. Similarly, when it is 2, you are getting 8, when it is 3, it is 9. So different number of rings we are getting. So here we are seeing that the observation, that is the percentage yield of this endo product. Exo product is not shown here, only endo is shown. That percentage is increasing when the value of N is increasing. That means that in the product side, when we have started with substrate where N value is 1, that is when with increase in the tether, increase in the length of the tether, we are getting a higher member ring from 7 to 8 to 9. And yields are also increasing. And that is written here, that yield of the endo product is increasing when the size of the ring in the product, that is increasing. Next observation, when we have large ring formation, 13 or greater. So if you see in this molecule, this is our Ci bond, that is the alkyl halide part, right? And this is the alkyl. Now there will be connection. Now here the product that we are seeing, that is basically endo product. Fine, because here it is written that for large ring formation, Heck reaction becomes endoselective, and we can use this strategy for macrocyclization strategy. So if you put numbering 1, 2, 3, 4, you will see it is ending at 16. That means we are getting a 16 member ring. So it is more than 13. So that is why it is endoselective. So in this way, we can form some, that is this strategy of macrocyclization. It is helping us to form this type of large rings. Then we have another substrate where 2 different product possibilities are shown, and from the color you can understand that this CC bond, it can be formed here. In this case the double bond is inside and PD will be connected to this side. Fine. Another possibility is if it is like this, which is the blue shown with the blue color, and this is giving us a 4-member ring. So 2 possibilities are there. 4 exo, 4-member ring. This is a newly generated ring, and in the right hand side we have 5-member ring. So 5 endo cyclization is generally preferred over 4 exo cyclization. Though we have seen before that smaller ring formation, it is for 5, 6 and 7-member ring, it is exoselective, that we have already seen. But here we are getting 4 exo. So 4-member ring, it is not very stable, and that is the reason in this case we are getting this is preferred over the 4 exo, because this is a very small ring. Finally, we will compare intermolecular and intramolecular Heck reactions. So in case of regioselectivity, intermolecular process for electronically neutral olefin That means if any group is attached to the alkene substrate, if this group is not very strongly electron donating or withdrawing, in that case it will be neutral olefin and regioselectivity will be a problem. But if it is intramolecular version, then it will be mainly governed by the steric consideration. And that is the reason we can expect high regioselectivity compared to intermolecular process. In intermolecular Heck reaction, only mono or disubstituted olefin we can start with as a substrate. So it will be like this, that is mono substitution, or it may be disubstitution. Suppose two R groups are already attached. But if it is intramolecular case, now we can use tri or tetra substituted olefin, because now the Rx, that means the halide part or triplet, and the alkene part, now they are part of the same molecule, so they are already close to each other. But if it is intermolecular, now the Rx, it is separate and this alkene is separate, so they have to come close to each other, and that is the difference between these two. So in intermolecular case, we can use this sterically hindered CC double bond. Then the third point, in intramolecular Heck reactions, it is generally more efficient than the inter, because in case of inter, we are starting from two different substrate. One is Rx, another one is the alkene, and in the product, after coupling, we are getting only one product. But if you consider intramolecular Heck reaction, now the Rx and the double bond, that is part of the same molecule, and that is the reason, as if from one substrate we are moving to one product. So this is the reason it is, from entropic point of view, it is more efficient. And finally, examples of asymmetric intermolecular Heck reactions are relatively recent, rare, and it is not very general. Very few examples you can see. In one of the videos that you will find in the description box, I have given asymmetric, that is asymmetric version of intermolecular Heck reaction. You can see the example. But if it is intramolecular asymmetric Heck, though I haven't discussed it yet, because this video, it is only the basic presentation about intramolecular Heck reactions. In the upcoming videos, I will focus on intramolecular asymmetric version. Then you will be able to understand in a better way. But if we compare the asymmetric intermolecular Heck and asymmetric intramolecular Heck, then obviously you will find that it is more developed for a wide variety of substrate. So that's all for this video. In the coming videos, I will discuss some examples of intramolecular Heck reaction. This is only the very basic for the intramolecular Heck reactions, and also the asymmetric version of this intramolecular. So that's all for this video. Thank you for stopping by.